more about differential forms, but actually a bit of a different take or sort of direction than what we've done before. I spent a lot of time talking about how it involves physics, and when you put this in space-time and do a clever sign switch, which I never really explained very much, you get all electrodynamics in just a couple of equations. Well, I want to go back to the basics of forms and think more like a mathematician. And a few years ago, I made up these homework problems for the end of a vector calc class about how you start doing the basics of topology using vector calculus ideas and things like Green's theorem and Gauss's theorem and Stokes' theorem. So what I'm going to do is I'm going to work through that, and I'm going to do it in parallel with vector calc notation and also the differential form notation, because the differential form notation is going to unify, as always, is going to unify all the vector calc stuff. So take a look at this if you want to pause the video for a second, if you actually want to read that. We're going to be looking at the connection between the topology of a universe, some sort of space to live on, and those can be fairly complicated and abstract, but for us it's just going to be a region in the line, the plane, or space, at least until we maybe think more about forms. A link between the topology of that and what kinds of functions and vector fields can live on the space. Okay, so we're not going to worry about differentiability assumptions and that kind of stuff, but we're going to deal with, we might have functions or vector fields that blow up at a point, but the way we're going to deal with that is we're going to declare whatever point it blows up on, or line, or plane, or whatever, as not being in our space. And M really stands for manifold, and these are going to be very special kinds of manifolds, but that's why I use the letter M here. Okay, we're going to start really, really basic. And so if these first ones, as always, because this is a homework set, if you have any familiarity with vector calculus, or even in the first one with calculus, you really should stop and pause and try to do these yourselves, or at least think about them yourselves. And these first ones, if you get really highfalutin about it, you're definitely overthinking it. So we start in one dimension. Our first manifold, we call it M sub 0, M naught, is just the real line. A very natural place to live, coming from one variable calculus. This is a connected space, and it has just one piece. And to be more precise, as I say here, any 2 points can be connected, can be joined by a continuous path. Well, duh. It's an interval, A and B, and it's the interval AB. In a bigger space like R2 or R3, it's a little more interesting. Okay. So let's consider a differentiable function on M naught such that the derivative vanishes everywhere. So we'll just turn this into a graph. Well, if the derivative vanishes everywhere, can't be very interesting. Okay. It's just going to be constant. But how do we know that? Well, it's a pretty basic fact of calculus, but let's assume we know the fundamental theorem and use the fundamental theorem to prove this, even though it seems hopefully kind of obvious if you're up on your calculus. Okay. But it really is actually a very, very deep fact. Okay. So how do you prove something is constant? You could take the difference between the values at any 2 different points. That looks something like the fundamental theorem of calculus talks about. That's the integral from a to b of f prime of x dx. Oh, but you told me this was 0 everywhere, so its integral is certainly 0. And so f of b is going to equal to f of a. Okay. So what I want to point out is that this, we could also write this, put it over here, as the integral over the interval a, b of f prime of x dx. And in fact, using differential forms notation, that's the integral over this ab. Oh, shoot. I'm going too far down. I didn't realize. It didn't show up. ab of df. Oh, hey. And that's, of course, equal to f evaluated on the boundary. Hey, that's the very simplest case of Stokes' theorem. Okay. And what's crucial is that this 2-point set, a comma b, just the two endpoints, was in fact the boundary of, was equal to, I'll put it here, was equal to the boundary of this guy. And so here's a set, and in fact it really was, to be really careful, it was b with a plus sign minus a, because we used this with a plus sign, this with a minus sign. Remember, everything has an orientation, and with discrete point sets, that amounts to putting signs on everything. So b with a plus sign and a with a minus sign is the boundary of the interval ab. That might seem like a ridiculously complicated way to talk about this very simple thing, that derivative 0 means constant, but it's going to be the model for everything else. And where do we use the connectedness of M naught? That's exactly the fact that any 2 points can be connected. It's a statement about this, that these 2 points were a boundary. Okay. And so in particular, a function, we've got an identification between the set of some special kinds of functions, namely those whose derivative is 0. Okay, so this is a set defined by some condition on derivatives. That's bijective. It's one-to-one correspondence with a much simpler set, which is just the set of all possible constant values. That's just R. Okay. And one other way to say it is that one number specifies a derivative-free function. And that's going to be a model for later stuff. How many numbers do you need to specify some function defined by some 0 condition on derivatives? Okay. Okay, now let's get a little more interesting, but not ridiculously so. Let's stay in one dimension, and let's look at the real line minus a point. Okay. So we've got the real line, and we're going to take the origin out. And so that's not part of our space anymore. So that's our M1. And is it connected? Absolutely not. I cannot draw a path that stays within my space from, say, -2 to 3, for example. Now, suppose f is defined and differentiable everyone on M1, and that its derivative is 0. I know I'm not being consistent about my colors. I've never been good about that. So here's a function that's defined and derivative 0 everywhere on this space. It is not constant. Okay. How many numbers do I need to specify it? Now, 2 numbers are needed. That's interesting. This space had 2 pieces. 2 numbers are needed to specify a derivative, a vanishing derivative function on this new space. Now, what if you have M2 is the real line minus endpoints? And just to be specific, I took out, let's go back to green. What the heck? Let's take out 0, 1, 2, let's say 3. So 4 points removed. And how many pieces are there? 1, 2, 3, 4, 5. And the official term is components to this space. Okay. Now if I have a derivative 0 function, let's go back to red for that, I can have 5 different values. And so 5 numbers are needed to specify this function. Okay. So the number of numbers needed measures the number of components. Okay. So it seems like a very overly fancy way to measure the number of pieces of something. I look at all the possible vanishing derivative functions on this space, and I ask how many numbers do I need to describe that. To be a little more technical, this is the dimension. If you know a certain amount of linear algebra, this is the dimension of the space of functions whose derivative is 0. And that's just, dimension means how many numbers do you need to describe something. Okay. So that's what I summarize here. How many holes does a space have, or essentially equivalent, how many pieces does it have? And that's equivalent to how many numbers are needed to specify a certain kind of function. Okay. Now we go to 2 dimensions. And the simplest 2-dimensional space, we won't mess with it yet. We'll just look at R2. Let's go back to green. So here's R2, nothing taken out. And it's definitely connected. I can take any 2 points and I can connect them with a path. Could be straight, but it doesn't have to be. And a really crucial thing that hopefully if you've done the sort of basic vector calculus stuff with Green's theorem, you recognize the phraseology that it's simply connected. That if I have a closed loop, then that can be shrunk down to nothing. Or a related thing, it's not quite the same thing, But the way we're going to use simply connected, and I'll basically use it as my rough definition of simply connected, is that if I have a curve C, if the boundary of C is 0, how could it be 0? It could be if the start and the end were the same point, and they cancel out when I take the boundary. So there's no end point. So it's a closed curve. Then C is itself the boundary of a region. We're going to see that that's not always true, that not every closed curve bounds in other universes, other spaces. And I'm not talking about anything exotic. We'll see in the very next part about that. But this is a condition, and I'm going to roughly, this is abusing terminology, but I'm going to say take that as our definition of simply connected. Or it's going to be my definition of one connected. And the one is that you start out with a one-dimensional object, and you think about if it's boundary-less, does it have a boundary? And if this statement is always true, these two synonyms we're going to use for that. Okay, so what can we do with that? Well, let's see. First, we're going to use the consequence of just one of those parts, not just we have connected and simply connected. Let me use the consequence of just part of that. And it's going to be exactly analogous to the first one about one-dimensional spaces. I have a differentiable function with the gradient of f is identically 0. That's what that triple bar means, identically 0, just to emphasize that it's not just 0 at a point, it is the 0 vector field. Okay, if the gradient of f equals 0, I claim that means it's basically never changing. I claim that that is a constant function, but I want to be able to prove that real carefully. And so what we're going to do is, again, we're going to take 2 points, let's say P and Q, and we're going to take the difference of those. Oh, if we recognize that as FTC for line integrals, and again, if you haven't seen that, well, if you haven't seen that, why are you learning about differential forms? That's the integral over some curve C that connects them. Hey, how do I know there's a curve that connects them? Oh yeah, that's the definition of connectedness. So that's what we're using here, of gradient of f dot dr. And I'm assuming that that's equal to 0. And so, in fact, it's constant because I could connect any 2 points and show that their values are equal. But it's really using the fundamental theorem of calculus again, but now the line integral version. Okay. So notice that it's similar to what I was talking about with simply connected. I have 2 points, and I take them with opposite sign. That's what the minus sign does. That is the boundary of a curve. And if I couldn't connect them, I couldn't say it's the boundary of a curve. And we're going to see that in the very next piece. Okay. What about in differential form notation? We just say df equals 0, identically equals 0. And then this just becomes the integral, the f of q minus f of p is exactly f, quote, integrated, unquote, on the boundary of the curve C. And this just becomes a df. So not a big change, but it's just going to be, that's going to be more uniform over all the examples that we're going to do. Okay, now look at B for a sec. What set could we remove from the plane? That was M3 in my master sequence here. I guess I'm going to try and leave this for a minute. To create a space that's not connected. Various choices. Okay, we could just take out an axis and say it's everything but that, and say that's not in our universe anymore. Or we could take out a closed curve or any wiggly line, sort of wiggly curve that goes off to infinity, anything that genuinely separates the set into 2 dimensions. Okay, so now if I have P and Q on opposite sides, I can't use that argument, is this equal to the integral of df over C. There's no C that connects these things. That's the whole point of it being disconnected, is that there's no curve that connects P and Q. And in fact, hopefully you can pretty easily see that I could choose any constant value over here, like this over here I have the constant value 5, and over here I have the constant value 8. And there's nothing incompatible about that. Just because the gradient is 0, or equivalently its exterior derivative is 0, that doesn't mean that I can't have different values because I can never cross this thing. It's just two totally unrelated pieces, essentially. Okay. And so what's the set of all vanishing gradient functions? How many numbers do I need to specify it? I now need 2, 1 for each piece. So that's really, as I say, that's exactly analogous to problem 1. However many pieces our space has, that's however many numbers we need to describe a vanishing gradient function. Okay. Now, let's see. Okay, so we're still on M3. Let's go ahead and put back the axis and connect it back up. Okay. Just back to all of R2. So we can't have different values. Okay, actually, let's erase that. Okay. We can't have different values anymore. But now we're interested in a more subtle problem. Now we're not going to take a function. We're going to take a vector field with, I call it the scalar curl, and I realize that's not everybody's notation for that. And let's say that's identically 0. What that means is, as I think I've explained in earlier videos, if f is pi plus qj, it just means dq dx minus dp dy equals 0. One-form translation is that it's a one-form alpha on R2 with, guess what? Well, there's only one thing we can write. D alpha equals 0. It's a closed, called a closed one-form. I've used that notation, that terminology a little bit. Okay. And we'd like to show that in the vector calculus notation, we'd like to claim that f is the gradient of some potential function. Here, I'd like to show that alpha is d of f. Because, of course, d on functions just emulates it implants the gradient. And the terminology here is that alpha is exact. Okay. Well, whichever notation you want to use, it's very, very equivalent. Let's use Green's theorem, and I'm going to use the differential form version because I put this in the context of lectures on differential forms. Okay. I never used those axes, did I? Okay. So I've got this form, and you have these stacks, whatever picture you want of the form. That's our alpha. We know that d alpha equals 0, and the claim is we can use Green's theorem. Well, that's really just the generalized Stokes theorem, of course, to show that alpha is exact. Okay. Well, how could we do that? Okay. Well, we're going to have to use a little bit of our knowledge, not stuff that we've actually explicitly talked about so far in terms of the context of differential forms. The claim, here's the key claim, it's that if the integral of alpha over a curve equals 0 for every closed curve, then alpha is exact, is df for some f. Okay. I keep leaving this here, and I'm about to use it, but I really want the room. Okay. Let's translate that to vector fields, because you should have seen this statement in terms of vector fields. Here's the equivalent claim. The translation of that is that if the integral over a closed curve dot dr equals 0 for every, well, I shouldn't use that symbol, for all closed curves C, then f is a gradient. It's a conservative vector field. The sketch of the proof, if that's not familiar to you, is that if the integral over a closed curve is 0, then you also get the statement that the integral over any two curves are equal if C1 and C2 have the same endpoints. Let me put a little boundary here. That's an F. Okay. And it turns out that if this is true, you can actually use that to construct, using integration, you can construct this function f. And if you're worried about, well, I don't want to take that on faith, we're actually going to do a massive generalization of this to show this kind of, or similar result to this later when we kind of do this entirely in the world of differential forms. It's very elegant. But hopefully this might be somewhat familiar about analyses of conservative vector fields. If not, you should look in a book like Stewart for stuff about conservative vector fields. Or I have videos about this too. Look at my videos. And this is the differential form translation. Okay. So if you accept this, then the proof is very, very easy. Okay, we're assuming that d alpha is equal to 0, that it's closed, and we want to know that it's exact, that it's the d of something else. And what this claim says is if we can just show that it integrates to 0 in every closed curve, then it's going to be exact. Okay, well, if C is closed, so the boundary of C is 0, we're going to use the fact that R2 is simply connected. That means C is the boundary of some region R. And so now if we integrate alpha over a closed curve, in general, just because d alpha equals 0 and just because this is a closed curve, that doesn't mean, that doesn't mean this is going to be 0. But if this is a boundary, then we can use Stokes' theorem and transfer that boundary to a d, and then suddenly, oh yeah, that's equal to 0. Note the similarity to what we had before in the fundamental theorem of calculus. We had 2 points. We realized that as the boundary of an interval. We used fundamental theorem to push that to become a derivative of our function, and we knew that derivative was 0, and we get 0. It's exactly the same proof, just one dimension up. And that tells us that, in fact, the integral of alpha over every closed curve is 0. Then there's this big claim, which is admittedly is a pretty big deal, that then that also means that it actually must be conservative. It must be an exact one form. Okay, but I want to emphasize really this thing, not the stuff we had to hand wave about. That this statement is exactly the same as what we had in the one variable case. Okay, so we've used the simply connectedness now. Okay, and so let's look at what I say here in these notes that I wrote up years ago. If we take any function, we can construct a scalar curl-free vector field. Irrotational is a good word for that, by defining big F to be the gradient of the function we started with. And so what we've just discovered is that if I have a scalar curl-free vector field, that is a vector field defined implicitly by taking the scalar curl and seeing it's 0, then it must also be explicitly described as the gradient of a function. Okay, and this is a really important thing. It's a huge thing in mathematics of going between implicit and explicit descriptions. The scalar curl-free 0 condition is good if I have a vector field already and I want to test it, but it's not great for constructing something. On the other hand, starting with any function you want and taking the gradient of it is very explicit and will construct a scalar curl-free vector field. The interesting thing about R2 is that those are the same set. We don't lose anything by constructing a scalar curl-free vector field to be in this special form. That's not going to be true all the time, definitely. Okay. And then I point out here the problem 2a, just about functions and derivatives gradients being 0. It says a vanishing gradient function is an implicit definition, and an explicit definition is take a number and create the constant function. Okay, and so this is the theme. One of the big themes that we're going to have is explicit versus implicit descriptions. Good place to stop this rather long video.